Okay, I thought that for this we would do just a little introduction to Gpower. It's incredibly powerful. So really and truly, the best way to learn Gpower is to play around with it and fiddle and experiment and ask a whole lot of what if questions and what happens if I do this. And it's fantastic. It's also good. I mean, it helps. Trying and experimenting really helps develop your quantitative reasoning skills, which is critical as researchers. So, but I can still do a little introduction. So power is your ability to detect relationships, if indeed they exist, and you've known that since you forever. And it's based on the type of statistical test you do. So first, you develop your hypotheses. You operationalize those hypotheses, and that leads to a specific kind of analysis. At that point, you're ready to run the power analysis, and you do it obviously before you collect any data because it'll tell you what sort of sample size you need to detect different effects. So Gpower is great. It's grouped. So the way sort of logically to go through it is to first pick what kind of test because they have different power. Excuse me. For instance, F, you could have, going to do an F test, you have all manner of different sorts of ANOVAs and ANCOVAs. Or if you've got T tests or something, then all manner of regressions and means and things like that. In your first assignment for this, just to get your feet wet, we just had a correlation. So we'll work with that and think about that. It's also kind of an easy, manageable case to think about. As we talked about, there's different kinds of power you can choose to do here. Typically in research, you'll use a priori power. You want to calculate what kind of sample size you need given your effects. So two-tailed tests are probably the best. Think about correlation. If you were to find a large regression coefficient in the opposite direction you predicted, it's unlikely you would ignore it. You would report it. So a one-tailed test would imply that unless it was the direction you said, then it didn't exist. So in terms of significance. So I would use two-tailed tests. Correlation, this little thing that looks like a P, that's a rho. And that is that's R. That's the population parameter for the correlation coefficient. And you can indicate the size you want to estimate. We're going to come back to that in a second. Typically we use 0.05 for the type 1 error. And our power, minimally we want 0.8. The null hypothesis typically is 0. There is no relationship, but I can see you could do something else. It's certainly the program allows you to. Now in terms of this, what size do you want to have enough power to detect? Well, it's good to do that in a sort of percent of variance. This is rho squared coefficient determination. This would be with a correlation coefficient. It would be the percent of variance shared. So this would say 50% of the variance was shared. That's actually quite a bit. Say for our purposes, we'd like to be able to detect 0.25. So we like to detect a relationship where 25% of the variance is shared. We calculate, that translates to a correlation coefficient of 0.5, and we can transfer it to the window here. You can go ahead and calculate. And this is, similar. You've seen these a lot. This red is the null distribution where there is no relationship. This blue periwinkle dotted line is the alternative distribution. So here in this little section, that's a correct decision. There was no relationship. You said there's no relationship. Over. This is this little blue part here, sort of the sad researcher area. Here there was a relationship and you missed it. You didn't have enough power. The type 2 error, a beta error. This little section right here is the divide by 2 because we're using a two-tailed test. This is the type 1 error. There was no difference and yet you rejected. You said there was a difference. So that's type 1 error. And all the rest of this here is power. There was a relationship and you were able to detect it, which is fantastic. So the goal is to get this blue line here, this curve, push it over to get it on the other side of this critical value as far as possible. And you do that by increasing sample size, by having large effects, by minimizing error. Those would be probably the three primary. Well, with that in mind, then, it's good when you're planning research to go ahead and look at sort of what ifs. So here we've got, this is a fantastic thing here. So here we've got power on the y, function of x on the sample size on the x, our correlation values. We draw the plot. It gives you the top part. It's very helpful. Two-tailed test, null is 0, 0.05, and we want to have enough power to detect a correlation coefficient of 0.5. So what this is saying is here's 0.8. You look at where it intersects the line, and you could drop it down. It's about 28 people. That would probably never be enough. You wouldn't say, okay, done, I'm going to collect data from 28 people, because this is an estimate. You just don't know. You would always try a few different scenarios, and you would always hedge your bets and get a few more people, at least a few more. And I don't want to operationalize and say how many more, but not 300 more, but 10 more, just to be careful, to be on the safe side. So you can also, there's so many things you can do here. You could also say, well, I want to plot the correlations, power, and I want to plot correlations here. And so this is saying, say I only had 29 people, and let's just, I don't know, let's make it 30. It'd be kind of weird just to have 29. So if I have 30 people, what's reasonable? You might say, well, there's no chance on Earth you're going to detect a tiny correlation. But gee, with 30 people, you might be able to get a correlation of, what about almost 0.5, a little over 0.5. But what about if you have, say I had 100 people? Well, that looks a lot better. Of course it would. Sample size increases, power increases. So if I have 100 people, that's great. Then look, I can detect a much smaller correlation coefficient, somewhere between 0.25 and 0.3. I can detect perhaps a correlation coefficient that explains less than 9% of the variance. So, and we could be crazy. Let's just be silly for a minute and say 1,000. Not that you would do that. Well, gosh, if you have 1,000 people, my goodness, you can detect a tiny little relationship. So typically you would look at what past research had done. You would see what's reasonable amount of data for you to collect. And then you'd say, well, if I could only have, say I could only collect data from 50 people, well, what's reasonable to expect in terms of finding relationships if they exist? Well, if I can only collect data from 50 people, then, probably I won't be able to detect anything less than a correlation of 0.4. So I'd only be able to sort of detect 16% of shared variance. And it could be the case that that's just not enough. Well, that means you need more samples. So I'm hoping that you're seeing that it's a matter of looking around, to come up with a good sample. It's a matter of trial and error and just practicing and thinking. And I have to say it's a fantastic way to learn, is just to say, what happens if I change this? What happens if I change this? So say you're happy that this is what you want to defend. So it's nice. You could say copy the plot. You can go to Word. You can paste it. And then you've got it in your document. So in your proposals, whether it be a grant proposal or a thesis proposal, you can put the plot in your section on power analysis. So, when you're writing a proposal, you'll have, your hypotheses, of course, and you'll have your analysis plan. And then part of the analysis plan is your power analysis. So you can easily pop this in and then use it as a guide to help explain what you're doing. So I hope that this is helpful. I think that this is clearly a program that's best played with and experimented with. But I'm hoping that this is helpful in terms of stopping the worry, or maybe phrase more positively, encouraging you to fiddle around and try things out. So as always, keep me posted on what's helpful and what you would like to see. So enjoy.